Good morning, everybody. Welcome to this morning session. My name is Frederick Mayer. I'm from ATR in Zurich, and I will be chairing this session. The first half is on Rydberg states in the condensed phase. And our first speaker is Matthew Jones from Durham University.
Okay, thank you, Frederick. Thank you to Stephen and the other organisers for inviting me to speak here. I was just saying to Stephen last night how nice it is to have a conference which cuts across all of the different things that you can do with Rydberg. It's a while since we've had one of these more general meetings, and hopefully this emerging direction of doing Rydberg in semiconductors. Before I plunge into my talk, just a slight note. Some of you may be aware that I used to work, I still do work on strontium Rydberg atoms. I'm not going to talk about that today, so if you want to know more about what's going on there, then just follow me in the topic. Instead, today I'm going to talk about how we can do Rydberg physics in a crystal. And this crystal is just a gemstone. You can buy it from any one of your favorite gemstone specimen suppliers on the internet. And nevertheless, here we can start to do some of the amazing things that we've learned from the atoms, and that's the main theme. So this project is a collaboration between Durham and Rydberg University. So in Durham, myself and Stuart lead the project, and the work I'm going to start today was mainly the work of Liam Gallagher, who's now a postdoc with me, and John Pritchard, who's just finishing a PhD thesis. And in Rydberg, the project is led by Stephen Lynch and Wolfgang Langbein. We also have collaboration with the group of Hamid Hardy at St Andrews. So Hamid was supposed to come and give a talk here, but unfortunately was unable to make it, but I will touch on some of the work that he's doing in my talk. And we collaborate with Valentin Balter, who's going to follow on after me with a talk more on the theory of the sort, and also Peter Grunwald. And we have some in-house theory support from Robert Poppy there. I also want to highlight this guy on the end. But it will become apparent towards the end of my talk why he's going to be very important to the future of what we do. So here's what I'm going to tell you about today. The motivation of it, what we're doing through something that we haven't heard a huge amount about at this conference, one of the directions that came out of Rydberg Physics, which was Rydberg quantum optics. And then I'm going to draw the analogy between Rydberg atoms and these things in solid state that we call excitons. So just to start doing that, this top spectrum here is the Bauer series of hydrogen as measured by Shaw-Lovett-Towns for Encyclopedia Britannica. And the spectrum below is ordered in like that. So you can see the background rainbow, that's different LED. And these dark absorption lines are signifying the presence of pure balance system, which in this case is an electron. And this Coulomb balance is because it's got a 1/r potential, we see the eigenstates of a 1/r potential. So rather beautifully, the existence of this quasi-particle in the solid state, this thing called an exciton, manifests itself by this direct analogy of the spectrum in hydrogen, which has obviously often been called the Rosetta Stone of quantum physics. So I find this direct correspondence absolutely fascinating. It's been known in semiconductor physics since the 50s. People first observed this exact experiment, essentially, was first done in Russia in the 1950s. But there's been an explosion of work since 2014, and I will try and explain to you why this system has got so exciting. What we're really doing in my group is looking at coupling microwave radiation to these excitons, so looking for the giant dipole moments between the excitonic energy levels. And then I'll give you an outlook of where we're going. So let's talk a little bit about Rydberg nonlinear optics to begin with. So the boundary Rydberg states, of course, lies in these enormous dipole matrix elements, right? The dipole matrix elements, the neighboring states of opposite parity scaled to n squared. And it's this that underlies very strong van der Waals interactions, which are used in all the tweezer array quantum computers. It's this that underlies all the microwave and electric field sensing that people are doing with Rydbergs. And so this is really where the magic lies. So these are up here in the Coulomb well, where the levels are very closely spaced, and the frequency corresponding to these transitions is in the microwave region. So at first glance, it seems that this is maybe not the best place to do optics with radiation of optical frequencies. But what you have to do, and this was kind of worked out in the early 2000s in Durham and elsewhere, is you have to map this strong interaction down to some strong transition between the line states. So typically this is done by using two laser fields. So this would be called a probe laser field, and then you would have a strong coupling laser field here, which couples you to some excited state. And now you map this strong dipole-dipole interaction onto the photon of this probe transition. So this is one of the first experiments that was carried out by Stuart Adams in Durham, which I was briefly involved in. So if you have this free-level scheme, you get an EIT feature here. But if this upper state is a Rydberg state, because of these very strong interactions, you don't have to increase your probe power very much before you see this EIT feature disappear. This is a nonlinearity. As we vary the probe power, the absorption spectrum is changing. And this happens because the Rydberg blockade means that as we increase the density of Rydberg states by increasing its probe power, we blockade the system, and the scattering properties of the medium are changed because I can't put any more Rydberg states into this band. And after 15 years of work, this is kind of one of the examples of the state of the art. So this is a measurement where they measure the second order correlation function, G2. So a G2 of 0 corresponds to the most non-trustable states of light that we can make. And in this experiment, using this mechanism in an extended medium, so a cloud containing many atoms, you can reach a second order correlation function here of less than a percent. Okay, so this is now a way of getting extreme optical nonlinearity that is quite well established. However, it's not the first way that people learn how to do quantum optics with Rydberg atoms. And we heard from Michel Brune yesterday. We gave a beautiful talk about circular Rydberg states. This is from Sergio Roche's Nobel lecture. So Sergio Roche won the Nobel Prize in 2012 for carrying out, along with David Wyman, the first experiments with single quantum. What they did in their experiment, along with Jean-Michel Raymond and Michel Brune, was use circular Rydberg atoms to supply and couple them to extremely high force factor microwave cover, so that they could coherently exchange single photons with this cavity where they could be stored for milliseconds and the Rydberg atom. Here they're directly exploiting these enormous microwave dipole moments that you get between high end Rydberg states. And with this, then they shrunk the fat states, gates, all sorts of beautiful experiments that laid the foundation for quantum optics and quantum communication. So what we want to do in this oxide, in this semiconductor material, is this kind of quantum optics, both times, in fact, and see how many of these concepts we can carry over to atoms to this semiconductor. Okay. So why can you do Rydberg physics? First glance, it's pretty unprepossessing. So you have this crystal here. It's a very simple crystal, really. Cu2L is a cubic lattice structure. It's a semiconductor with a band gap of about 2.2 eV. And as you know from your undergraduate physics, semiconductors do not have hydrogen-ionic energy. So they do not have Rydberg states. They have bands. And so at first glance, it seems that this Rydberg physics should not carry over at all to a semiconductor. As I've already alluded to, the trick is that what happens when you excite, when you shine light from the valence band to the conduction band, and we say that it leaves behind a hole. So both of these things, the electron are essentially quasi-particles, right? They're delocalized across the whole lattice, and they're used with an effective mass given by the curvature of these bands here. With these bands are parabolic, they look pretty much like particles moving in free space, but just with the mass replaced by the effective. But the key thing is that this electron hole can lower its energy by being closer together, because full attraction is positively charged hole and negatively charged electron. And that potential, apart from a screening factor, which is due to the background dielectric constant of the crystal, not in a vacuum, that inside the crystal, is basically the same potential, and we get the same potential, we get the same spectrum of energy. It's an analogy between the exciton and the hydrogen atom can be drawn rigorously mathematically, so you can go from Bloch wave functions to these exciton waves. So if you look a little bit more in detail at the spectrum, then what we find is that the analogy is actually quite good. So here we have the P series of cesium, and the excitons that we generally look for in cuprous oxide are P excitons. They have a similar opportunity. So here we have vacuum. We have full Rydberg constant, so these are quite far apart in energy. Here we have dielectric screening Rydberg constant, and so the spectrum is kind of scrunched up. Here, the conduction band that Stewart provides is like the ionization quantity Rydberg atoms. So if we go higher, less in energy, and the big difference is that we find a very broad and asymmetric excitons. This is because they become non-negative by emitting phonons, which is, of course, the decay channel that's not available for cesium. So why is this field suddenly got so exciting? You know, about 1950. Well, the answer is this paper that was published by the Durham University in 2014, where a very high quantity synthetic sample now N=30, and they've stored the first ever blockade through suppression of excitation in this material. Why is this such a big deal? Well, this graph that I'm showing you here is the current gas value of cesium for a continuous system in the solid state. So you can make quantum dots. If you want to take a continuous medium, in this case, electron to gallium arsenide, this is the current best value of G. So you have to believe that this light blue bar here is less than all the others. And this is the only evidence so far for to produce non-classical light. So if you remember, we had less than percent of the atoms. So if we can map these strong attractions between these electrons onto light, then perhaps we can do non-linear optics in the solid state. Be a very, very deal, and I think that's what Valentin is going to talk about mainly. So we want to look at these strong dipole conditions being with the same opposite parameters. So we want to excite electrons, P state, for example, apply microwave radiation, see if we can drive these. Do they have these large dipole moments the same as we see in hydrogen atoms, or is there something about this background dielectric or about the spectrum with carriers that actually it's not the same? What can we do with this? Can we do some experiments similar to what Serge Roche and others pioneered? And one of the reasons you might want to do that is that microwave technology is kind of playing the resonators. So you're probably all familiar with these systems. Superconducting qubits are linked together by microwave transmission lines and resonators. There's a great effort to couple these things to light so that quantum information is transmitted out of these computers to operate at tens of millikelvin. So maybe we might have to talk about this because we could do that. I did say that there's a lot of work underway doing this, trying to do this with ATAMP 2. So here I've highlighted an experiment Stephen Hogan's group at UCL here, where they're trying to find atoms in the metastable helium beam. I think Joseph Fortag is going to talk about this tomorrow, where they're using trapped atoms and related work in a number of groups around the world. Okay, so now I'm going to talk to you about our work. Trying to learn about what really happens. So here's how we do our experiment. We take a natural gemstone, which as I say, we buy from gemstone suppliers on the internet. So these originate in Africa, is where the highest quality specimens are found. We use X-ray to get the correct crystallographic orientation. We slice these pieces and then polish them down to the thickness of about 100 microns, which we need to do because the absorption rates in the material is very short. We're going to melt them in the proper amount, and this goes into a closed-cycle primary Kelvin. And to get the picture that I've already shown you, all we do is illuminate this with an LED close to the band gap and disperse the light in a grating spectrometer. So we can do better spectroscopy by using a laser. So we take we amplify and frequency double the light into PPLM to get tunable, very narrow band light at the band gap. And then we measure the amount of light that goes through the oxide on a seeing protein sample detector. And if we do that, then we can get this spectrum here. So here you see a really nice Rydberg series 6, 7, 8, 9, so on. If we zoom in, you can see that we can clearly see at least 15 P in this case, possibly 16 P. This is mainly limited by the fact that our sample is at probably about 5 or 6 Kelvin. If we could get colder, we would see a higher. Doing. I'm conscious that atomic physicists don't speak EV. I didn't speak electron volts. So here I've added the scale bar. So say here, 7 P and 8 P are separated by approximately 100 gigahertz. Obviously, the states are much closer together than higher. Now, what we're going to do is apply some microwave radiation to goal of driving these transitions to these other states should exist if you believe this of excitons, and using other spectroscopic techniques, people have measured the presence of these parts. So to apply the microwave radiation, we have a simple antenna. It's just a strip line. There's one wire here. There's another wire on the back that we can't see. So this makes a capacitor. The cuprous oxide is in the hole here. And this is supposed to be a relatively broadband structure, which lets us apply microwaves at lots of different things. We just made it copper for the moment. So if we do that and we turn on the microwaves, then we see that the spectrum changes. The purple spectrum I've already shown you, the spectrum includes here. And what you see is that the high end peaks are essentially largely suppressed. But they're not suppressed here. They don't get suppressed down to the bottom here. They kind of suppress at the midpoint. So it's like we've moved oscillator strength from these P resonances into the gaps here. And that's where these S and D states are. So this is evidence we're mixing the states together. And if you take a difference, so that's what this sketch illustrates here. We have this strong microwave field now, and it's mixing all these states together. So these S and D states coupled to the light now do couple to the states. So that's what's happening here. And then the P states couple a bit less because they've now got S and D character mixed in. Okay, so this is evidence that we're mixing the states together. And if we take the difference between those spectra, then you can clearly see that we have those enhanced absorption, and we have reduced absorption on the P states and enhanced absorption between the location of these S and D states. So a key point here is that this system is very different from atoms. So here the microwave frequency we're implying 7 gigahertz is much less than the spacing between these states in this region of N. And yet we still see this strong microwave effect. And we see it over a whole range of states. So we're not coupling to one individual Rydberg state here, we're coupling to all of the Rydberg states. And the reason for that is that the microwave frequency that we're applying is roughly the line of the state, so that's typically a 10 gigahertz, which in turn is roughly comparable to the energy separation between states. So in some sense, we're in this quasi where the microwave frequency is not far reaching from any of these transitions. And so it's able to derive all of these transitions. What this means is that unlike atoms, we have an extremely narrow band. Here we have a very broadband frequency response. But measuring the change in absorption is not. We can also resolve the frequency spectrum of the light that's transmitted through the sample. So to do this experiment, what we do here is add a scanning throw epsilon here. And so now what we do is we scan the frequency of the, so we fix the frequency of the laser, and we scan the frequency of the epsilon, and we measure the transmission. And what we see then is that as far as the carrier frequency here, so this is just what we get. No microwaves are careful. When we turn the microwaves on, we get these side bands that twice the microwave frequency. Okay, so here's the frequency of 7 gigahertz, the side band is 14 gigahertz. And these are very weak, but nevertheless, there is very clear second order side band. So we are modulating the light. There's a cross current on the guarantee here with a microwave field and the opposite. As we increase the microwave power, we see the second order side band here. And if we drive hard enough, then we can use fourth order side band here as the second order side band. Go down. So we've made a Kerr effect electro-optic modulator. So can we gain a bit more understanding? Can we be more quantitative about this? Can we extract whether or not the dipole matrix elements, for example, agree with the sort of atomic theory of these excitons? Do we understand what's really going on? So to do this, we've constructed a model. So the model is a model which produces the molecular susceptibility of the medium at the carrier frequency and also at the microwave sideband. And the model has a number of ingredients, so we need to know the energy of those even and odd parity states. So these come from experiments. And we need to know their width, which is we also get by physics. We need to know the dipole matrix, the prediction of the dipole matrix element between these states of opposite parity. And these come from calculations made by Valence and Valter, which are based on this hydrogen exciton picture, but correcting the wave function for the curvature of the true curvature of the bands. So these are really atomic, coming from an atomic picture, assuming that the exciton picture really holds. So those calculations use input to state energy to affect the dielectric constant and the effective masses of the electron. And we need to know the strength, the coupling strength of the valence band to the Rydberg state, which again from the experiment. And the key again is that because we're in this quasi-resonant approximation here, we cannot apply the rotation rate approximation. So we must use the counter-rotating terms. And the theory I'm going to talk about mainly today is determinative in the sense that we restrict the maximum number of microwave photons exchanged to 2. So this theory only really describes the second order sideband. So it's a weak field theory for what's going on. If we do that, then we can make a plot that looks like this. So at low field strength, this is our data, the change in absorption. So I already showed you this curve where we take the difference between microwaves on and microwaves off. The red dots are the experiment, the red lines are fit to this susceptibility model, where the only parameter is the electric field strength. Okay, so given the number of independent C parameters derived elsewhere for spectroscopic measurements, so the agreement is actually pretty good. Certainly for solid state quantitative prediction, this is pretty good. And you see there is some resistance, but they're relatively low. So low microwave field strength, this physics model seems to explain what's going on pretty well. There are some discrepancies where we don't quite match but overall the agreement is reasonably satisfactory. I think. As we increase the electric field strength and the agreement gets worse, we understand why this is. I'm not sure I have time to talk about this today, but if you ask all the questions, I can explain to you what's going on. We understand what's happening today. And then if we go to higher field strengths, then we find that this perturbative model is massively underestimates changing numbers. So for today's talk, I want to focus on the flow. What we're going to try and do is extract phase shift that corresponds to this cross-phenomenon, corresponding curve coefficient. So what we do is we note that at this point here, shown by the dotted line, that there's no change in absorption. Any sidebands that we see are coming from the phase modulation part only. So in general, we can have phase and amplitude modulation given the sideband. But at these points where there's no change in absorption, any sidebands that we see are coming from phase modulation. So we measure the relative height of the sideband fraction of the carrier as a function of the microwave field strength. And then using the standard theory for phase modulation, where you have a better function and so on, that depends on the amplitude of your modulation, you can extract corresponding phase shift on the right. So we get a maximum phase shift of about 0.1 radian here. And then if you know your microwave field strength calibration, you can convert this into something called the curve coefficient, which is basically the amount of phase shift per unit length per unit field squared in your meter. Okay. And so that's what we experiment with red dots here. This is the curve coefficient. I'm looking at the different points where we have these zero options. There's one that we missed. So there's a missing data point here. You can also calculate this curve coefficient from the model. And we find that that's a very good agreement with the red data points. And what I want to point out here is that the units. So here we have about 21. These units of meters per volt meter per volt squared. And this is the table from a paper Kerr coefficient of the meter. So I want to draw your attention to the fact here, they multiply all the Kerr coefficients by 10 to the minus 18. Okay? So this value here for Rydberg apple down here will be 10 to the minus 6. We have a Kerr coefficient of 3.1. So we're still working on this analysis, but we believe that this is one of the biggest microwave optical Kerr coefficients ever measured in any So what are we going to do next? Where is this all going? So one of the questions that should be worrying you is that if you've got the biggest Kerr coefficient, I've told you that we've got, but we have tiny side bands. So these two things seem to be incompatible. If I've got this giant Kerr coefficient, how come I can't get a bigger phase shift? Why can't I get bigger side bands? These things don't seem to match up. And the reason why they don't match up is because of the phonons. So one of the things I noticed when we did our Rydberg section, you might have noticed was those Rydberg states were sitting on a background. Okay, and actually this background is enormous. So this is what the sort of full spectrum over a much bigger scale looks like near the band gap. And so the Rydberg section is up here. So everything I've been telling you about so far is in this little region. And they're sitting on this enormous background here. And this background is coming from processes which involve absorbing a photon and emitting a phonon. So this curve here, the stratified shape of the background, is essentially the negative states of the phonons in the medium. And because I'm emitting a phonon in these processes, I can't get rid of this at low temperature. Even if the modes are empty, if I write down no phonons in these modes, I can always emit into these modes. So we always have this background process where we're absorbing photons and emitting a phonon into the mode. And that's an independent process. There's no Rydberg character whatsoever. The excitonic characteristic is low lying on S. So these states have no Rydberg character. They're very, very small. Rydberg wave functions cover many, many lattice sites. But the exciton involved in this process is of the order of a lattice site that doesn't cover the microwave radiation. So the only part of the transition that I can modulate is this little bit here. And as a consequence, the phase shift that I can even though I have this very large Kerr coefficient. Okay, so it's a slight cheat to say that I've made it into the largest Kerr coefficients ever observed. I can extract the Kerr coefficient, which is very large, but I have to bear in mind that it's rather than a transmissive medium. So we have to be a little bit careful what we claim. So at first glance, that looks pretty disappointing. It's very nice that we can modulate this thing, but how can we get? But it's not really going to be very useful if the medium is this lofty. But we do think that we have a way around this. So the way that we go around it is we use a different excitation scheme where we use two photon excitations in even parity states. So we create S2 states using a two photon excitation, so we get rid of the frequency governing crystal and just send our infrared rays straight into the cuprous oxide. And the cuprous oxide itself produces the second harmonic. So without the microwaves, that process is done by a quadrupole transition. But when we turn the microwaves on, because the microwave photon lets us change the parity, we now get dipole allowed processes involving the exchange, in this case, of plus or minus one microwave photon. So this is not a Kerr nonlinearity, this is actually four-way mixing. So I have two photons here, infrared photons here, and then one optical and one microwave photon here in this four-way mixing process. And the advantage of this process is that it doesn't suffer from this phonon background. Okay, so when we measure the spectrum of this second harmonic generation process, there is no phonon background. And now, if we look at the spectrum, what we find is that here we're modulating 19 gigahertz sideband of first order, and you can see that we can get sidebands which are comparable to the size of the carrier. Okay, so in this case, we can really strongly modulate this second harmonic that's coming out. So this seems like cheating, and the cheat is that we have very high time because the second harmonic generation process is very weak. So we have to pump the system quite hard, and we're sort of filtering out the limits and just looking at the can generate the second harmonic. But nevertheless, we can use this for efficient microwave optical conversion in the and that's what we're looking at doing going forward. So we can take that spectrum. So in the game of microwave optical conversion, the plot that everybody has is a plot like this: efficiency. So efficiency here is the number of optical photons per microwave photon. So this tells you straight away that to get high efficiency, you have to pump your medium. Because if you're going to convert one microwave photon into one optical photon, you have to get the energy from somewhere. All of these interfaces are pumped, so it might not be such a problem that our second generation needs a strong pump power. And the bandwidth of the conversion. And so we have the advantage of very high bandwidth, which comes from these broad excitons, their short lifetime. And for the spectrum that I showed you, our current efficiency is about here. And what we hope is to drive this up. And so one of the things that comes into this plot is the mode volume of the microwave photon. So the mode volume of the volume in which the conversion is taking place. Because obviously we have this huge antenna that's several centimeters long. So just by having a much better antenna with a much better confined microwave, these hollow points here are the only ones which have done anything close to the quantum. So the noise is low enough that you can consider doing quantum conversion. So I just want to say a little bit more about this bandwidth. What it is, and again, this is coming from a large language of states that we have, and that we're sort of talking to all the Rydberg states at once in a way that's very different from atoms. So this is a measurement of the second harmonic process, the four-way mixing process that I showed you. So here you see the Rydberg states. This is the Rydberg series going across here. This is the optical energy. And then this is the microwave frequency. And you see that we're getting, then this is the change in across this range of microwave frequencies. And these sharp resonances that you see are just resonances in the antenna. Okay, so if we have a different antenna, we see a totally different set of sharp resonances. But the underlying dependence is very low. And if we go on our acceptability model predictions, you see that expect the change in the principal number, the higher principal number, the more sensitive at low microwave frequencies, because the states are getting closer together. So where are we going next? So I mentioned Simon Doyle, the mystery man, in my first slide. So Simon Doyle at Cardiff, his expertise is in manufacturing of lasers for single photon detectors in astronomy. So he can make arrays of thousands or even millions of high T-factor niobium or aluminium resonators across a whole wafer that can be used in these kinetic inductance detectors. So he's an expert in the microwave resonator technology at superconducting temperatures. So we're going to collaborate with him to produce these complicated structures. So we're going to collaborate with him to integrate our cuprous oxide with these superconducting resonators and see if we can do microwave optical conversion using this hybrid platform. We also need to improve the coupling efficiency device. So we're collaborating with the group Hamid. Hamid was the first group to observe strong coupling between an optical cavity, an optical microcavity, and Rydberg excitons. So in these gallium arsenide games, you get these photon dispersion curves here. These are the dispersion curves of the counter nodes, and these black lines here are the absorption lines. And you can see the characteristic anti-crossing here near the exciton resonances. That's the signature that the exciton is strongly coupled to the optical cavity nodes. So we've already started to make some optical devices with this group, and we hope to gradually start integrating these together with microstructures in a kind of long-term project. And also at Cardiff, we're investigating using laser machines to control the local environment around the exon, so to trapped. The excitons can be trapped by strain. So this has been observed over 30 years ago. It's a sort of macroscopic strain gradient used by pressing lenses on samples. But we want to engineer the strain locally by damaging the material, by shining eyes to it. And so these are some examples of the change in absorption you can get by shining these tightly focused lasers. And with that, I will finish.
So we did find that the string is actually broader than the spaces. It's comparable. Then we cannot think of an orbiting period anymore. It's a bit like the alkalization air gas. What people use is standard for modern fuel. This continuum is about
so the line very symmetric. Produced by three electrons. But the kind of predominant theory really is coming from how they the structures that are micro field strength from then yeah. And more than. So this is why it took out long. So we've also done a more involved model, which is based on clocking theory. So you published a similar paper to this. So this is where you allow much multi-photon processes essentially to include up to 50 photons exchanging here. And you basically fully diagonalize. Rather than doing this perturbative susceptibility model, you do a full diagonalization up to some order where you cut it off from the photon number. Do that, then we get plots like this, where this is the experiment, and this is okay. So and so in the previous the previous graph I showed you, the thing broke down in about 50 millivolts, 50 volts. Now I've actually been told there's a factor of 2. I got found this out this morning thanks to my team. They sent an email saying, "Oh, there's a factor of 2." Great. But this should be 600 volts per meter power. So we can go up to 600 volts per meter and basically get, I would say again, pretty good qualitative agreement between the theory and the model. So what that means is that we understand this breakdown of the model as multi-photon process, which is what you expect because of this all resonant character. You expect the multi-photon process to be very important. And I think we're seeing sort of up to 10 photons, plus or minus 10 photons going on here. So we're really in this ultra strong driving regime, which is interesting, right? Of this sort of yeah. So there is a quantum effect, that's the yes. Modeling the energy. The origin of this quantum effect is quite different. So in that case, it's so short range effect. Here, slight non-parallelicity of the band. So the band is not perfectly parabolic, and as a result, it's not perfect. Because it's not perfect, the degeneracy state is broken. And that has been calculated by people who do band structure theories. And and they've shown this explains the origin of this. Yes, yes, well. Yeah, essentially the same thing, but in that sense, the short range effect here is essentially an everyday effect. So this is a subject that comes up a lot. It's well understood why this works so well in cuprous oxide. So that the ingredients you need are nearly parabolic bands. So you need a cubic lattice, nothing fancy with weird stuff going on. It's more or less isotropic. So cubic is close to spherical as you can get in the solid state. But if you want exon lines you can label with atomic, I mean these are approximate labels, right? I should really have gamma 8- and things like this on these labels. They're not really S, P, and D, but these approximate atomic quantum numbers work very well. You want a high exon binding energy, which cuprous oxide has. And then cuprous oxide also has a forbidden gap, which means that these exons have the p, which is why they have p symmetry. And this means that they're not washed out by an enormous kind of strong coupling to light. So people are looking at materials like tin oxide, which has a larger band. Not immediately obvious that this is having less problems with the phonons. So currently the dominant trends for getting rid of the phonons are non-linear spectroscopy, like what I showed here. So Valentin is proposing the ITAMP scheme, for example, to get rid of this thing. Possibly doing phononic engineering with the material. But there is certainly, and in GMBCs, they've seen up to n=5. So these exons don't really look like atomic physics exons. So I think there are probably other materials, but to really see n=30, I'm not so sure that you can see that in.
So it looks, yeah, no further. So let's thank Matt Jones for this. Now because the theory part and university.